So in today's class we will be seeing the multinomial naive Bayes algorithm, and we will see an example which we saw in the previous class very briefly. We will see this in detail again, and then we will see how do we evaluate the machine learning models with the help of precision, recall, accuracy and F-score. So in this example you can see we are having the training data and the test data. So this is the training data and this is the test data. We are having 4 documents in the training data and we are having a single document in the test data. So the naive Bayes classifier is actually a lazy classifier. Lazy classifier means that actually there is no kind of the training, but all the parameters are calculated during the testing time. So when we have this test document, we will calculate the parameters of the model on the basis of this test document, and we won't be calculating the parameters of the model. That is the parameter table. We have these parameters, so we won't be calculating these parameters for all the training data. So the reason for this is that for a given test document we don't need to calculate all the parameters. Like we have this Shanghai, so we don't need to calculate the conditional probability of this Shanghai, because this does not appear in the test document, right? So in this test document the contribution of only those words is required which are present in the text document from the training data. So we will see in this training data and test data, if we take this Chinese, Tokyo and Japan, so this Chinese is occurring 3 times, right? So in this we can calculate the probability of Chinese and then multiply them 3 times, right? So the probability of Chinese given C, P of this Chinese given C has to be calculated, then it will be multiplied by again 3 times. We can take the power of 3, then P of Tokyo given C, then P of Japan given C, then P of the class C. So this is the probability that will be the P of class given D5, right? So this is the P of class. Which class we are concerned about here is actually the C class. So this is the probability of class C given the document D5. Similarly we can have the P of class J given D5. So we will just replace everywhere in the same formula. We'll just replace the C by J, and here also we will replace the same thing given J, same parameter given J, and we will multiply with the prior of J, right? So in order to calculate these probabilities, P of each word given the class, so we require this formula. This P of W given C is actually the P of, actually it is the count of word and class, and we are applying the Laplace smoothing. So we are adding 1 in the numerator and we are adding V in the denominator. So if we calculate V is the set of unique words that are present. So V is we are having Chinese, this is 1, and then we are having Beijing, this is the second one, and we are having Shanghai, this is the third one, this Macau is the fourth one, Tokyo is the fifth one, Japan is the sixth one. So we are having a 6, V as equal to 6, that is the unique words, is the number of unique words is 6 here. So the count WC means that given a word W, how many times it is appearing in a given document. sorry, how many times it is occurring in the training data for that particular given class C. So we will just only see in these three documents which belongs to class C, and will have the count of word W. So if the word W is Chinese, so we will count the Chinese is occurring how many times in class C document. So this is 1, 2 and 3. So we are having this value as, sorry, this is 4. So this is 1, 2, 3 and 4. So I am having 4 plus 1 for the Laplace divided by total number of words in that class is 8 plus 6, right? So in this way we calculate the probabilities for all the given words, and then we finally calculate the probability of that given particular class using this formula. So the probability of C given D5 is probability of Chinese given C. Probability of Chinese given C is 3 by 7. It is occurring, the document is occurring, the word is occurring 3 times. So we will just take a cube of this, and then we have Tokyo given C. Tokyo given C is 1 by 14. So this is 1 by 14 is here. Then Japan given C is 1 by 14. So 1 by 14 is here. And then we are having P of C is 3 by 4. So P of C is also 3 by 4. That is equal to 0.0003. Alright, so we have done this for class C. Similarly, we will do the same thing for class J. We will be calculating in class J how many times the Chinese have appeared. So it is 1 by 3. So when we apply Laplace, it becomes 1 plus 1 by 3 plus 6, that is 2 by 9, and there are only 3 words present here. The probability is 2 by 9 for all these 3. So we will be having 2 by 9 for all these 3 words. The Chinese is occurring 3 times, so we will multiply it by 3 times, and then the probability of Pj is equal to 1 by 4, that is 1 out of 4 documents here. So that will be equal to 1 by 4. So we get a probability of 0.0001, and then we compare these two probabilities, and whichever is high we predict that class. So in this we will be predicting the class C. Right, so I hope this is clear to you people, that how a naive Bayes classification is working with the help of these Laplace smoothing. So if we don't apply the Laplace smoothing, so if we have some kind of, say, suppose new word here that is present in the text document, so in that case, suppose I have a word here that is present, that is China. So when I am calculating the probability of P, so this additional word, this P China given C has also to be calculated. So P China given C, when I will look into the training data, then I will not find this China here. So when this China is not present here, the probability comes out to be 0. So P of China given C is equal to, now if you apply the Laplace, it will be equal to 0 plus 1 divided by the count of class is 3 plus 6, that is, it will become 1 by 9, right? So in this, so this is actually, sorry, 8, so this will become by 14. So 1 by 14 is the probability of that particular word which is not present in the training data. So in this way, the probability that is coming out to be 0 will not be 0, and if it is 0, then we will not be getting any final value of the class given the document. So that's why we try to make it non-zero with this Laplace smoothing. And Laplace smoothing is a very basic kind of smoothing. We have other kind of smoothing techniques that are much more efficient. So hope you have understood this. Now this naive Bayes can be applied in lots of applications here. So we need to just see what are the different features that can be taken into consideration. Now we are having this in this example, we are using the words as features, and in respect to words, the language model is actually the bag of words. We are just seeing in the text document we are seeing what are the different words, and then we take that word and go into the training data, and in training data we actually see the bag of words. So in case of this Chinese, we see that this is the bag of word, and then with the help of this bag we calculate the probability, right? So this is the simplest way of text classification, but in order to enhance the model in order to make it more efficient and more robust to the different kinds of settings, the different kinds of environments, so we need to add some more features apart from these bag of words or n-grams, etc. So we can use different kinds of features depending upon the type of problem we are having. So in case of spam filtering, we may have some kind of, like, if the subject is all capitals, we may have add a new feature to our model. Similarly, we can have some kind of, this kind of, if this kind of notation or this kind of expression is present in the email, then we can have this as a feature also. Similarly, we can have some kind of like URLs that are not very common, or that are having some kind of uncommon things that are, so we can use these as features. So if this is the feature set, original feature set here, so that is bag of words, so this is the bag of word 0, bag of word 1, bag of word 2, bag of word 3, and we are having bag of n words. So we can now again add some more features. So this is again feature 1, this is feature 2, this is feature 3, this is feature 4. So what we did in the previous case with the help of bag of words was, this is, suppose this is the document 1, I will write the count of the document here, this is Chinese. So I will write the count here 1. If it is word 1 is not occurring, I will write the count as 0. Similarly 2, 3 and 4. Similarly, I will see now in these features also I will apply the same thing. I will count how many times this feature is occurring, or if it is a binary feature, I will just see that whether it is occurring there or not. So if this f1 is binary and it is a URL, so I will just see that whether URL is present or not. So I will just mark, if it is present I will mark 1, if it is not present I will mark 0. Similarly, if the subject is all capitals, for the next feature I will see that if that kind of subject is present, with all caps I will mark 1, otherwise I will mark 0. Similarly, I can have the count of URLs that is present in the email. So if the count of URLs or some kind of hashtag or some kind of mention in case of tweets, something like that, so we can do those kind of, we can take into consideration those kind of features as well, right? So in this way we enhance the feature set, and by enhancing the feature set we enhance the model, right? So live Bayes algorithm is a very basic algorithm. It's not a kind of that algorithm that would do the best thing with some data. So, but the good thing is that it is very fast, and it has very low storage requirements, and this naive Bayes is robust. Also, robust means that it works with all kinds of features. So there is nothing like that with some kind of features the algorithm will not work, or the algorithm will perform poor. So naive Bayes is actually not so poor and not so good algorithm. So it's kind of an average algorithm. So that performs average on all kinds of data. So to start with any problem, naive Bayes is a good algorithm. So we can use this naive Bayes, such a kind of baseline, algorithm to compare with other algorithms. So this naive Bayes is again a good baseline algorithm for text classification. Now let's see how do we evaluate a text classification algorithm, or in general this evaluation method will be applicable to any kind of classification algorithm. So the parameters that we use in classifying or in evaluating a machine learning model is normally we calculate the accuracy. Right, so we draw a contingency table also called as confusion matrix. So confusion matrix is actually a 2 by 2 table for a binary classification problem. So in case of binary classification problem, we are having either the predicted class is correct or the predicted class is not correct, right? Or this is the true labels, these are the true correct class, and this is the true not correct, and this is the predicted, and this is also the predicted. Right, so in this table tells us that these are the total number of true classes. True classes means if this is positive and this is negative, we are having two classes, positive and negative. So these number of training examples TP, that is true positive and false negative, these are actually the positive classes. So true positive means that the positive examples have been truly classified as positive. So that's why they are called as true positive. So they are predicted as true as well as actually they are also true. So this is actually true and these are predicted true as well. Predicted positive, actually true positive is predicted positive. And this false negative is actually predicted as negative, but in true it is not negative, it is positive. So this is actually true. In ground truth it is true, but it is predicted negative. So predicted negative means that this is actually not negative, so that's why we call it as false negative. Right, similarly we have this false positive. False positive is in actual it is not true, in actual it is not correct. So actually true it is, actually true is that it is predicted positive, and this actually true is that it is predicted negative. So this true positive is actually true as well as it is predicted to. This true negative is actually true and it is predicted negative. That means the original class is negative class and the predicted by the model is also the negative class for these samples. Right, now the problem is with the false positive and the false negative. So when we say the false, it means that the system is showing that it is positive but it is not actually positive. Right, so predicted positive means that it is actually true negative. I must write it as actually true negative, but it is predicted positive. Actually true positive, true negative, and it is predicted negative. Similarly, this is positive and this is positive, right? So this is false positive. False positive means that it is predicted by the system as positive, but actually it is not positive. Similarly, false negative is that it is predicted negative by the system, but it is not actually negative, it is positive, right? So when we calculate the accuracy, so accuracy is equal to all the correct predicted labels, predicted correct labels upon total. So what is the predicted correct? Predicted correct is true positive and true negative. So this is TP plus Tn divided by TP plus FP plus FP, sorry, Tn plus Fn. So this is the accuracy. This is also called as the recognition rate. Recognition rate means that how many examples are recognized correctly. Right, so the problem with accuracy is that it's not a very good evaluation measure when we have the imbalanced class problem. So in imbalanced class problem, we are not able to see the correct working or the correct evaluation of the model. So how this is actually occurring, that it is happening that the accuracy is not able to show the actual results. So let us take some examples. So suppose we have a problem of recognizing, say suppose animals, and we have two classes, right? So we have one class is that the particular given image is of an animal, and the other class is the image of not an animal, right? So suppose in our data set we have a small number of animals and we have large number of non-animal images, right? So the data set is like this. We have animals as very small number and non-animals as very large number. Suppose the large number is say 10,000, right? And animals is only 10 here, or say 100. All right. So this true class for the correct one for animals will be, so this total will be 100, right? So this correct class, this total will be 100. So if I say that among the 100, if the model is able to predict 50 as the correct animals and 50 as non-animals, right? So the predicted from 100 examples, the system is predicting animals as 100 and predicting not animals as, predicting animals as 50 and predicting not animals as 50. And from these 10,000, if the model is able to predict not animals as 9,900 and it is predicting animals as 100, or let's take 50 here. So this becomes 9,950, right? So now what is the accuracy? The accuracy is 50. According to this formula, accuracy is 50 plus 50, the accuracy is 50 plus 9,950 divided by 10,000 plus 100. So this is 50 plus 50 plus 50 plus 9950. So this is 10,000 divided by 10,100, right? So you see this is almost very high figure. So you can calculate it is almost around 99%, right? So this turns out to be 99%. So we say that our system is 99% accurate. But we see that with respect to the animals, we are having only 50 as predicted correct animals, and among those 50 animals it has not predicted as correct animals, it has predicted them as non-animals. So this kind of evaluation method is not correct. So for that we have the precision and recall. Precision and recall. So precision is actually the percentage of selected items that are correct. The percentage of selected items that are correct, it means that the items that are predicted correctly from the total number of predicted items. So it means that items, let me write down the formula. So that is TP upon TP plus FP, and this is TP upon TP plus Fn. So precision is this TP divided by TP plus FP is this. So total number of predicted is TP plus FP. So that is, this is total predicted and this is correct predicted. Similarly in recall, this is the TP and this is TP plus Fn. TP plus Fn is actually the true class. So this is total true, or in this terminology it is called as correct, total correct, total correct and predicted correct. Right, so these predicted correct and correct predicted is the same thing. So we see here the precision is taken into account in such a way that we are able to calculate the fraction of the correct predicted from the total number of predicted samples, right? Whatever it has predicted, the precision is the correct among those. So in our previous example, the predicted for this true class or the predicted for animal class is 50 and the total number of true animals is 100, right? So total number of true animals is 100 here, and among 100 it has predicted only 50. So the precision for our example is 50 divided by 50 plus 50, that is 50 divided by, this is this is 50, this one, right? So this is 0 or 0.5 or 50%. Precision is 50%. Similarly, recall is equal to true positive 50 upon 50 plus 50. So that is 50 upon TP plus Fn is again 50 plus 50. This is again 50%. So now you see that here in this case the recall is actually among the true classes how much it is able to recognize correctly. In all the true from the data, so if this is our data, so from this data I am having this 100 as animals, so this is the 100 samples of animals, which is the true data for 100, true data of animals as 100 samples. So among these 100 samples, how much it is able to recognize as animals, that is called as recall, right? And the precision is how much it has predicted, in that how much it is able to predict correctly. So it has again predicted the 100 as animals, right? So this is the true data. If I draw the table for predicted data, it will be also same. It will be also same because animals, so this is true data and this is the predicted. So animals, it has predicted 100 as animals, 50 as correct and 50 as not correct. So this is again 100 and non-animals is again 10,000. So from the predicted outcome of the class animals, how many are correct? So from predicted class animals, 50 are correct, so the precision is 50%. Similarly, from the actual true class animals, how many it is able to predict as animals, right? Predict as true animals. So this is the total number of animals, true animals, and it is able to predict only 50 as animals. So that is called as a recall, right? So in this way we are able to, in actual sense, evaluate a machine learning model, right? And when we compare it with the accuracy, we see that the accuracy for this kind of settings is 99%, but the precision recall is quite low here. It is only 50%. So there is some kind of trade-off between precision and recall. If we somehow we are able to we manipulate these values, the false negative and the true positive ones, so you see these are the same, this true positive is same here and this true positive is same here. The problem is with the false positive and false negative. So this false positive, it means that the correct class is going in not correct class. Similarly, the correct class of negative is also going in the not correct class of negative class, right? So whenever we see that these values manipulate, so if this from the total figure, if this turns out to be low, might be possible that it is going into this one, right? So if we are able to somehow increase the precision, we will see that the recall becomes low. And similarly, if we are somehow able to increase the recall, we will see that the precision becomes low. So these two are actually have some kind of trade-off between each other, right? So in order to eliminate the trade-off, there is a parameter that is called as F measure, with the help of which we maintain the trade-off and we take the actually harmonic mean of both precision and recall. And when we put the value of beta as 1, we call it as F1 measure. And with the help of this 2pr upon p plus r, we calculate the F1 measure. Similarly, we can put the different values of beta here and we can get F2 measure and F3 measure, but in general most of the people use F1 measure only, right? So in this way we are able to calculate for binary classification, we are able to evaluate with the help of accuracy, precision, recall and F score. But what happens when we have more than two classes, that we have multi-class classification, right? So in that case, we can have this kind of contingency table. So in this contingency table, this is again a problem of text classification, in which we are having 6 classes, right? So the documents are based on UK, poultry, wheat, coffee, interest and trade, and the system is classifying the documents into these 6 categories, right? So this is the true one, and this is the predicted one. So we see here that in this case, the true coffee is 34, and the system has also assigned 34, right? So the true coffee, total number of true coffee example is 34 plus 3 plus 7, that is 44. So among 44 examples, the system has predicted 34 as true, but the system has predicted the 3 coffee labels as interest labels and 7 coffee labels as trade labels. So these are actually coffee. So what we would call these as? So these are false negative or false positive. So these are actually positive, but they are, by the system, they are given as negative, right? So these are false negatives. These are not negatives, right? Similarly, for all these for any class, for any class. So if we are interested in coffee, so we will be looking in this row and this column, right? So again, it has assigned coffee as positive to some other true document, so it has assigned 13 as coffee. So it means that this 13 is, by the system, it is given as coffee, but it is not actually coffee. So this is false positive. This is also false positive, right? So system is saying it is positive, system is saying it is coffee, but it is not coffee. System is saying it is coffee, but it is actually trade, right? So with the help of this kind of seeing only row and column, we can calculate the precision for coffee. So what is the formula here? We see that the precision is TP upon TP plus FP. So precision is true positive is 34, TP upon TP plus FP, that is 34 upon true positive is 34 plus false positive is this total. So 34 plus 13 plus 14. So 34 plus 13 plus 14 is 61. So that is 34 by 61. So this is around 56%. So this is 0.56. Similarly, we can calculate the recall for coffee, that is true positive upon true positive plus false negative. So this is again 34 upon 34 plus 3 plus 7, that is 34 by 44. So this is around 77, 0.77. Right, so in this way we are able to calculate the precision and recall for individual classes. Right, so we see again here that that the precision is how much in total predicted it is predicting the correct label. So the predicted is 61 and it is predicting correctly is 34. Similarly, in recall, from the actually true labels, the true labels of coffee is 44 and how much it is predicting correctly is 34. Right, so we can do this the same thing for all the classes. So we will get here 6 precision values and we will get 6 recall values. Right, so in order to calculate the average precision and recall, I can just do is that I can take an average of all these. Right, so that will be a kind of micro averaging technique. That will be a kind of compute the performance of each class, macro averaging. So if we compute the performance of each class and then calculate the average, that is called as macro averaging. Right, but if we collect all the decisions of the classes, that means I am collecting all the true positives of all the classes. I am collecting these values and adding them. Right, so these 95, 1, 0, 34, 26 and 10, so these are the true positives for all the classes. I add them all together. Similarly, I will calculate the false negative, that is these values for all the classes, and I will add them all together. I will again calculate the false positive for all the classes and I will add them together. So in this way, when I am calculating the precision and recall, so that is called as micro average precision and recall. Right, so we can understand that with the help of this small tables. So for I write the contingency table for the classes individually. I write the contingency table for the coffee here and I write the contingency table for UK here. Right, so if I am calculating the precision individually, as we calculated just in the previous example, so individually calculating the precision and then taking the average is like this. Right, but if I add the true positives like this and generate a new contingency table, I add all these values, and in this way I arrive at a new contingency table, and then with the help of that contingency table I calculate the precision or recall. So that is micro averaged precision. The problem with the micro averaged precision score is that it is dominated by the class that is having high predicted values. So here we see that this class 2 is having highly predicted true positive, so this will dominate. So that's why the average will be close to the highly dominating class. Right, so in most of the cases this macro average precision is used. So apart from macro average precision, we are also having weighted. So weighted, actually we count the total number of samples that are present and then we multiply with its individual precision or recall. So that is called as the weighted, that is according to the number of samples in that class. Right, so in this way we are able to calculate the micro averaged and macro average precision, recall and F score. So these are again general settings. We have the training data, we have the test data, and we do require the development or set data or development data, so that we are able to test our model and we are able to set our parameters, we are able to optimize the parameters. So we use the development set. Right, similarly we can have cross validation, which means that we can have this kind of different kind of settings of these training and test development. We can have different kind of samplings with the test data and development data, or test data or training data. Right, so for this part I have taken as the training data here, and this has taken as the development data. Similarly, we have taken another sample, this part has been taken as the development data, this in another, this part has been taken, and so we are able to generate different models with the help of different samplings of the same data, and then we calculate the we calculate the average of all these, right, and then we can get the average performance, or we test the data on all these, and then we see whichever is giving the best performance, we finalize that model. All right, so with the help of cross validation we can get an average performance from different models, as well as we are able to select the best model out of the different samples of data. So you have any questions here? Okay.